Why they are interesting? They are interesting because if you don't have Taylor series, you will never be able to calculate e power x on computer. Just think about it. Because they give you a way to approximate these crazy functions, transcendental functions, crazy numbers, to something which are finite in polynomial. It's something easily computable.
Those beautiful equation e power I of I plus 1
Is
also a consequence of this divergence. E power I of I plus 1.
yeah, listen.
At first, e power I plus theta is not significant. Not bigger plus I.
From that way you are saying. You can drive e to the iota theta from. It's like you take the Maclaurin series of sine theta and cos theta and multiply series with iota and sum them. And that's it. Series play a crucial role. It's like you have something very stupid or something very crazy, but it turns out that you can kind of approximate that crazy object, that crazy wave or that crazy function, okay, through a bunch of very simple objects. So in that way, it plays a very important role. And it's very important then that what is meaning of the convergence of series. In other words, if you add loads of things, what is meaning of basically making sense of that huge sum? If that sum is going to make some sense, like you have a huge sum of something, you add that, is it going to give you a picture, something concrete? You're going to say that the limit is something concrete that you get out of that each sum. Anyway, there can be loads of interpretations. Series are important to be used. Must be useful. So our task is to define this guy. Take all from 1 to infinity. We're going to have immediately, get the symptom of this notation.
Infinity.
What's infinity? What's infinity? What is the meaning of adding something to the infinity? Does it make sense to basically add something to infinity? That's what we want to define it. I mean, in limits of the sequence definition, if we write actually that limit n equals to infinity a n in a, we really understand that what does this mean? This means that after a particular instant, for all terms, the distance between this and this is going to be really small, going to be very minute. So we say that this actually means the way we have defined this. So that definition is kind of a meaning of this symbol. That's an abstract symbol. Abstract equation. So similarly, this guy is an abstract symbolism. What does it mean? What is the meaning of adding lots of infinite number of fractional real numbers? What's infinite in first place? This course is all about the wrestling with infinite. It's nothing. It's just from the beginning you're just trying to wrestle with infinite. Alright, so let me introduce a notation Sn. And Sn has a meaning that we understand. Imagine I have a sequence. I have a sequence An. An is sequence. N is sequence. By Fn, I mean the sum of the first n terms of this finite terms. Like k equal to 1 to n and k. I hope that there should not be any trouble with this statement. This doesn't make sense. So we can already see that for every S1, what will be S1? S1 is going to be A1 and S2 is going to be
Even plus A plus
A2. A1 plus and so on. We can already see that. So we're gonna call that as what? What are the name rules for this one? So we call that's a partial sum. Okay. That's a partial sum of the terms of the sequence element.
Cumulative sum. Cumulative sum.
Cumulative sum. Cumulative sum. Partial sum. I mean, if you observe interestingly, this sequence S1, so it's like this S1, S2, Sn, like it goes on, itself becomes a sequence.
Yes.
It's like this S1, S2, S3, that's like a sequence of the partial sum. Okay. Do we get it? So, by this symbol, so that's a symbol actually. Don't treat that as a sum. And this is equivalent symbol. And I would like to define as that what is the meaning of the convergence of this symbol, the abstract symbol that we have. So I have a sequence and partial sums and the sequence of partial sums. Now this sequence of partial sums may converge or diverge. So if it is converging and it is converging to something, then we're going to say that yes, this abstract symbol or abstract series, we call it, is converging. And it's converging to what? That number which is the limit of this sequence. Also, we're going to say that an infinite series, this infinite series, n equal to 1 to infinity, n is convergent. Converges to a number S if this sequence of partial sums as an push.
There is a ghost.
And why that's a sensible thing? Just think about it. Imagine I have Sn. It is a sum of I equal to 1 to n ai. And I'm saying that take limit n approaches to infinity of this. So in other words, I'm going to say that take the limit n approaches to infinity of this finite sum. That k equal to 1 to n and jk. So as n will get bigger and bigger and bigger, this sum is going to get bigger and bigger and bigger. So to this I am denoting it by
Initial.
Are you getting the point?
Yes.
So what I am saying, इसका मतलब क्या है? इस symbol का मतलब है, symbol का मतलब है that you take this partial sum and take its limit. You take its limit. This limit may or may not exist. I don't know. So it can be convergent, it cannot be convergent. If this converges, we're going to say that this symbol or this sum infinite series converges. If this diverges,
तो इसके बराबर है, तो ये इसके बराबर
in other words, if this makes sense, then it makes sense to replace this n by our abstract symbol infinity. It's like, if you see what is the difference between this expression and this expression, you have an n here and you have an n. Goes to infinity, so you can write infinity. Okay. So it's just a symbolism. This is just a symbolism. There is nothing. There is nothing like infinite series. So, right? We define infinite series as the limit of the partial sums. This are divergence. Small pillar. So how many of people are happy with this definition? How many people are really understood?
Understood, not actually.
First of all, we're going to say that I would like to define this symbol. In order to define this symbol, I'm saying take this sequence, take its partial sum. The partial sum is going to be its self-sequence. And this limit of this partial sums, whether it is infinite or finite or whatever, I'm going to give that limit a name actually. That limit is this. Are you getting the point? I'm going to give that limit a name which is infinite series. Then I'm going to say that this infinite series converges if the sequence of partial sum is converging. And this infinite series diverges if the sequence of partial sum is converging. Simple. Okay?
Don't we have this epsilon n game here?
We will have, certainly. Because the convergence of this guy is depending on the convergence here. So we can bring in
the sequence.
this. So like right up here, which is what you say the Kashi criterion. Solution afterwards. It's like a Kashi criterion for convergence of sequences. Simple theorem. In one line of theorem, we're going to say that this sequence A and n goes to 1 from 1 to infinity will convergent if and only if for each epsilon bubble there exists capital N such that the sum of a k where I
I is the structure.
a k where k starts from n and is less than epsilon for all n
Greater than n.
m bigger than or equal to n bigger than or equal to n. If that makes sense actually.
So m bigger than n
Huh?
for all m.
Sir, m is bigger than or equal to. Okay. So thus I'm going to say that if I have to prove a series convergent, that's a criteria to prove. So in other words, take some partial sum. You just think about it. So that's a partial sum which starts from an arbitrary point n, and arbitrary goes to an arbitrary point n. So I can take this n and capital M as much as large I want, and this sum, okay, can always be bounded by a small number. So if you are able to do this, for all n and m after this basically it's Proof is self-evident. There is nothing difficult in this. Just think about it. So I'm saying that imagine this is a convergence. So in other words, I'm saying that this guy and equal to 1 to convergence. What does this mean? This means that take the sequence of the partial sum. That is, this sequence of the partial sum has n, where n goes from 1 to infinity, is convergent. And hence Kashi. This is Kashi actually. I can directly say it's Kashi. So this is convergent. If this sequence of partial sum is a Kashi sequence, and we know that every Kashi sequence converges to one. I can either call it Kashi sequence, which is going to imply convergent or other. Okay. So if this is the case, then for every epsilon positive, I can always find n such that the distance between Sm and Sn is going to be less than epsilon for all m bigger than or equal to n bigger than or equal to n. 3. But what is this guy? This is exactly the same n. What is Sm? And then bigger than or equal to n is going to be S1 plus m. When you are subtracting the first n terms out of it, so we're going to have
Yes, sir.
N prime.
okay. One side is easily true. Why the other side should be true? In other words, you can bound all of terms basically. It's going to be, the output is going to be, because if this is true, then this Sn is going to be a Kashi sequence.
Directly going backwards.
Exactly going backward actually. It's going to be a Kashi sequence, and since every Kashi sequence converges, so
This can converge and then plus.
Yes, we have to find. It's interesting that this is still not true. Let's get back. Better days. I haven't wrote it informally. I haven't written it informally. So I said that I have infinite series, and by infinite series I mean a sequence, take its partial sum, and take the sequence of partial sums, and limit of this sequence of partial sum I'm going to denote it by this symbol. And equal to 1 to infinity. Okay. And if this sequence of partial sum is convergent to some s, as n goes to infinity, I'm going to say that the series is converging to s and going to. So that's what my definition is. So if Sn converges to S, it must be Kashi, and I can have something like this. Okay. So I can go backward exactly. So if this is true, that means that Sn minus Sn is less than epsilon for all n bigger than or equal to n. This means that Sn is Kashi. This means that Sn is convergent. This means that series convergent. So you can go exactly. It's really self-evident. This follows from multiplication. So I would like to end
Sir,
a very interesting observation.
Sir, we have written that S infinite series converges, so Sn converges some point S. But we are not using that point S in our definition.
But the issue is this, that the good thing about the Kashi sequence is that forget about limits. Forget about limits. I can also define this as that the infinite series is convergent if Sn is a Kashi sequence. Okay, just assume that. Because if it is Kashi, it must converge. Convergent is. You can play the way you want. Either you can say that okay, the series is convergent if the sequence of partial sum is Kashi. Fine. Then it's convergent. Last thing. and here. This is a very interesting observation, easy and interesting observation. And tell me that why this should be true. And tell me that why this is an interesting observation as well. So try to take out that interesting thing from this statement for yourself. Help me out with this. So I'm saying that if and equal to 1 infinity converges, then and approaches to infinity is zero. Why this proposition is a very interesting proposition? Yeah.
It's contrapositive.
Contrapositive is very interesting. What will be the contrapositive? If you want to prove that some sequences, some series is convergence, just take its, the representative of the sequence and check that whether that limit is zero or not. So if it is not zero, this must diverge. But if it is zero, it may or may not basically. It may converge. That's about this. But the contrapositive is for sure. This is something very good. And therefore you call it divergence test.
Not convergence test.
Not this divergence test. Huh? Call it divergence test. You want to prove some series divergent, take its representative, take limit and just show that it is convergent. It's not going to zero. Even if it is converging but not converging to zero, it's going to diverge. Just show that it's non-zero. Why this should be true? Assume that the series is convergent.
Then it's a Cauchy sequence and
Assume that this series n equal to infinity a and converging. How we can drive that physically? So one of the things is going to be
take it as a Cauchy sequence, and since Sm minus Sn is less than for any epsilon, if we would follow it,
Sn minus Sn.
Sm minus Sn is less than any epsilon. So basically Sm and Sn are equal, and hence for any n and n they are equal. So let's call it m is equal to n plus 1. So you can.
That's what the key thing is. That's what the key. So why just go to Cauchy sequence? Why not to take that? Okay, if this is convergent, that this means that limit n approaches to infinity Sn is some finite number. It's a finite. And we say that take Sn plus 1 minus Sn. Okay. This is going to be what? Okay. And then take the limit on both sides.
N plus 1. It would be n plus 1, right? The resultant difference would be n plus 1.
If you want to
Yes.
take n, just add minus 1. So what would be this limit n approaches to Sn? It's going to be S. And what would be limit S approaches to S? It doesn't make any difference. Minus n. That's called divergence test. Carry on, beta. Okay. Have free days for 2 weeks. No. So I know that. I was expecting this. But especially